Hello and welcome. Today we're going to be talking about limits at infinity. And limits at infinity are are a little bit more tricky in the complex plane because we because obviously in a plane, if you're going to infinity, either uh, the idea here is we'll have limit z going to z naught f of z. We want to be able to make sense of this when the magnitude of w naught is infinite, i.e. it's undefined, or I should actually just put an arrow going to it, or alternatively that z naught is identified with infinity. Okay? All right, in either of those cases we have to make sense of what that means. So let's talk about an example that kind of highlights some of the ambiguity here. So first of all, let's take a particular example. Let's take f of z is equal to 1 over z. All right, so now z, if I want to take the limit z going to 0 of 1 over z, and I want to be able to make a statement that says that's equal to infinity, and I'll put quotes on that. And then what does that exactly mean? All right, so obviously what we have here is a problem of, like, we have multiple paths. Because we're talking about a two-dimensional plane, I should say many paths. Infinitely many, in fact, of z going to 0. For instance, you have, the idea here is you have z, and it's going to make its way in towards 0 from lots of different ways. Okay, and it could loop around, do whatever, but eventually it has to go in and take the limit going to 0 in the z plane. Right, and then with f, what we want to state then is in the w plane, somehow our limit, our w variable, is somehow going off out to further reaches in the outer edge of the complex plane. The problem is, of course, we can go many ways. So there's many ways to what I'll call infinity. And what does that mean exactly? It just means, because this is certainly a different route to a large modulus complex number. So certainly w in all these cases is the modulus is going to infinity, but there's certainly different paths. So this is a unique path to the outer reaches of the complex plane, and that would be another path out to the outer reaches of the complex plane. So we have to have some sort of language for talking about this ambiguity that's going on here. So let's talk about this example. For instance, now let's try two paths. I'm going to try path 1, which is going to be, let's say, just a particular, so we're going to take z to equal r e to the I theta 1. Okay, and I'm going to take path 2 to be z equals r e to the I theta 2, where these are fixed angles. Okay, and what we're going to do then is now take our limit, then in this case is going to be limit r now going to 0 of 1 over z r, and we want to make that be equal to something, so that's going to be limit r going to 0, and when we do the algebra, that becomes e to the I negative theta 1 for path 1 now. And now for path 2, we have the same thing, limit r going to 0 of 1 over r e to the I negative I theta 2. So for instance, if theta 2 is here, or theta 1 is there, let's say, and basically I'm going to go take this path going in like that. All right, and where's that path going to go? That's going to lead to negative theta 1, right? And that will be the path going out that way to infinity. Okay? Likewise, let's say if I have another one, a path here, that'll be theta 2. And again, my r is getting smaller, so I'm going in towards the origin there. And that will lead to a negative theta 2, and a path out towards infinity going that way. So clearly there's an ambiguity. And what we mean by this ambiguity is that if all paths lead to the same point, it doesn't make any sense. Because if I actually take these two paths, and I'm going to call that WR, call that W1R, and this I'm going to call W2R for the two paths. We can actually write that now. I'm going to write W1R minus W2R. All right. So I want to know, it should be, a limit should always work out that if you take two different paths, should get closer as R goes to 0, right? As we take R to 0, this should get small. But what we find is the opposite. What we do is if I put this in, so that becomes 1 over R e to the negative I theta 1 minus 1 over R e to the I theta 2. All right, and so now we can do a little algebra. The modulus comes out, and then we have e to the I theta 1 minus, or that'd be a minus there. There'd be a minus there as well, e to the negative I theta 2. Well, it's clear that as R goes to 0, this actually goes to infinity. So it's not small. The 2 points are actually getting further apart, and we can see that, of course. As R gets smaller, if this is sort of the distance between those 2 points there, I'm going to call that D, we can see that the distance gets bigger and bigger and bigger as we rocket off to infinity, because the two paths are diverging. They're going in opposite directions, or different directions away out into the plane. So clearly, our notion of limits is just flawed in the complex plane. So what we really want to state then is actually that the magnitude of WR, whatever path, 1 or 2, goes to infinity. That's what we want to state. We want to limit, a way of talking about limits at infinity that capture that aspect. So let's see if we can do that. Okay, so what we need is a little bit of kind of a new concept of the complex plane, and it's called a stereographic projection, or I should say maybe a representation. So that's a new representation. Okay, so what we're going to do is we're going to write this plane. So this is going to be kind of understood in 3D. So I'm going to draw the plane as a sheet living in 3 dimensions now. It's just a horizontal sheet now, and that's our complex plane. Okay, and at 0, so there's z equals 0 right there. Then I'm going to draw the unit circle. Like that. And now I'm going to essentially affix a sphere to the unit circle. So that'll be distance 1. I'm going to affix a sphere to it like that. And it goes underneath as well. Right, and up on the top there, that's the North Pole. And then put down here the South Pole. And you can put a little axis that it goes through there, like that. All right, so now with this sphere, I'm going to say basically what we're going to do here is we're going to essentially curl up the plane into a sphere. Spell that right, S-P-H-E-R-E. Okay, so that's a pretty wacky idea, and I remember when I first saw this, I was impressed by it. I thought it was pretty neat. Anyway, the idea there, and I'm going to fill in a little bit from the book. I'm going to make a little cartoon here. I'm going to kind of think of there as an eyeball right at the North Pole. I like to think of it this way. So maybe this is like, I don't know, in the Lord of the Rings, right? There's that Eye of Mordor that overlooks everything in the whole world, in the whole Middle Earth. So here we are in Middle Earth, and there's the Eye of Mordor who's sitting at the North Pole on the unit sphere, affixed to the complex plane. All right, so so what we're going to do then is like wherever the eye looks, eye points downward at a point. So that's my south pole there. Z in the C plane. So in this case, I'm going to look. It's going to It's going to look right there, and it's going to come down, and there'll be some point in the complex plane it's looking at. And that eye is right over the top of the North Pole there. So maybe I should draw it up a little higher. There we go. Make my eye a little bit bigger there. Okay. So it's going to pass through the sphere at one point, and also pass and hit the complex plane. And we're going to identify those 2 points. So we're going to identify Z in the plane with a unique point, a unique point on the sphere determined by the direction of sight of this eye that I've drawn up there. All right, so these 2 points are now connected, these 2 points are now identified. So I can talk about this particular value in the complex plane, and I can also talk about that same point as being positioned somewhere on the sphere. So for example, if the eye looks straight down at South Pole, then that is identified with the point Z equals 0, right? Because it's looking straight down, and it sees that point there at Z equals 0. Okay. Now, for points inside the unit circle, so if the eye looks down, sees a point inside the unit circle, it's going to be identified with points in the southern hemisphere, right? So there's the southern hemisphere, and there's some point there on the southern hemisphere that's identified with every point in the unit circle. So also then points outside the unit circle, so points out here, are also identified with north, the northern hemisphere. Okay, so that's really nice. So now we have a representation. So what we've done essentially is we've done exactly that. We've curled up the plane into a sphere. Okay, so what's nice about this now is if I have a really big, if I'm out here far out away from the origin, like this, as I get bigger and bigger and bigger, if I go further and further out, so I take Z going big, I'm going to put the modulus of Z as big. I can think of it as actually Z is actually greater than 1 over epsilon for epsilon small. So if I'm way out there, notice that every point of a large modulus is actually sitting very, very close to the North Pole. So points Z that are greater than 1 over epsilon, for epsilon being small, are near the North Pole. So now I'm going to say I'm going to set the North Pole itself, the point on the sphere, the North Pole, to be the point infinity. Okay? And so that now we have this notion of infinity as being the point on the North Pole of our sphere. Okay, so any z value that is very, very large in modulus, that's sitting outside, is getting nearer and nearer on the sphere to the North Pole. So that's a very nice way of representing or thinking about the point at infinity. Okay, so let's now use this concept to do some work, to do some limits. So what we're going to do then now is define the epsilon neighborhood of this point infinity, and we're going to call that actually n, the point infinity epsilon, to be equal to, so n infinity comma epsilon is going to be equal to the points z such that the modulus is greater than 1 over epsilon. Another way to write this, of course, is epsilon is that 1 over z is very, very small. So that's our way of understanding the point of infinity. So this is that neighborhood. So if I have that unit sphere in our stereographic projection of the complex plane, that point infinity then has a neighborhood, which we'll call that epsilon neighborhood, which is identified with the point with every value of z that's outside the radius 1 over epsilon. So every point that's out here in the outer complex plane that is bigger, that has bigger modulus than 1 over epsilon, is identified with this neighborhood at infinity, around infinity. Okay, so that gives us a nice way of thinking about the point at infinity. A way of now we have a way now to describe nearness to infinity. Okay, so now let's use this concept to compute some limits. So now we have some idea of how to conceptualize what infinity is, or that point at infinity. All right, so with this now, we want to go tackle limits. So we have this limit again, z going to z naught of f of z equals w naught. So where either z naught or w naught can be near, or sorry, can be infinity. And I put that in quotes again. Infinity means that we're talking about it approaches this smaller and smaller neighborhood of infinity. Okay? So now we have a way of talking about that. So of course we have three cases. One where z naught and w naught are both infinity, and two other cases where only a single one of them is infinity. Now we're going to talk about those two cases. All right, so let's go back and now. So if I have, so I want to talk about now. Let's talk about case. I'm going to go to the next page here. So I'm going to talk about those three cases. So we're going to have limit z going to z naught, and that's finite. F of z is equal to infinity. So we're talking about w naught being infinity. Okay, right? I want to make sense of this. What I'm saying then is, so what I want to make a statement then is that actually f of z equals w naught. That is actually going to be greater than 1 over epsilon for some small epsilon when when z is in the deleted neighborhood of z naught for some delta, right? Right, so that's another way of stating this, right? And that means for every epsilon I can find a delta such that in this deleted neighborhood the magnitude of f is really, really large, okay? So we can actually rewrite this as the following. And that's basically stating that, and that's sort of saying, i.e., I should say, that if f of z is going infinite, we could also say that 1 over the magnitude of f of z, right? We can just do this simple algebra is actually less than epsilon. Or otherwise we can state that it's going to 0. So our equivalent statement then, so I should write this, limit z going to z naught, f of z, is equal to infinity, is equivalent to diagnosing the following limit. So if I want to assess if this, for a given function that I'm given, if I want to assess if it diverges to infinity, I can actually check the following. I can take the limit of z going to z naught of 1 over f and check if it goes to 0. And that is a perfectly fine way of studying these limits. Okay, and likewise, we can do the same thing for limit z going to infinity of f of z, where that is a finite value. So what we're saying here is that z has to be bigger than some 1 over delta. Well, I'm going to be precise about saying that. I'm going to say f of z minus w naught is less than epsilon when z is less than 1 over delta. Okay. Another way of stating this, of course, is that we can also write this as delta is less than 1 over the modulus of z. So we can state this again as the following. So we can either evaluate this limit, or I can look at this case here. So what we're doing is establishing this sort of equivalence of, I could answer this question here, or I could answer this question, and they both are equivalent. One implies the other. And for this one, we see here we have that same relationship now. This approaches our limit, whatever this finite value is, when our z is getting very small. Or 1 over z, I'm sorry. 1 over z is getting really small. So we can do the same thing here. We can actually now take z going to 0 when of f of 1 over z. Okay? Of course, when 1 over z is when z is getting closer to 0, 1 over z is getting very, very large. So it really is equivalent to that, and that's equal to w naught. So the idea here is then, if you want to answer this question, if as z goes to infinity, f goes to some w naught, we could also recast the same question in the following way and study as z goes to 0. Okay? All right, so finally, we can put the two together. So the third case would be limit z goes to infinity, f of z goes to infinity. And we can put the two together and answer the similar question of limit z goes to 0 of 1 over f of 1 over z goes to 0. Okay, so if you want to answer this question, if this is true, you could also equivalently recast your problem as follows. All right, so now let's actually compute some. Let's do some examples really quick. Okay, so let's do some examples and finish up this video. So let's talk about the following one. Limit z goes to -1 of I z plus 3 all over z plus 1. Okay, and we see here down here there's clearly a division by 0. And it doesn't appear to be a division by 0 on top. So our candidate, we want to know, is this true? So what we can do is then recast our problem. Limit z goes to -1 of 1 over f, which is going to be limit z going to -1 of z plus 1. So we're going to invert this, right? I z plus 3. And clearly we can see that I can now put in 0 for both of these, and there's no division by 0. I have no problems. This function is continuous there. So it's clear that then this is equal to 0 because we can substitute the -1 right in there. For -1, we see that there's a 0 over a negative I plus 3, which is equal to 0. Okay. All right, now let's do another one. Now let's talk about limit z goes to infinity of 2z plus I all over z plus 1. And I see here that there's a first power of z in the top and a first power of z in the bottom, and so I'm thinking, well, really this looks like an infinity over infinity case, but I don't know exactly what it converges to. So, but I want to say it converges to maybe 2. If you just look at it, because the leading order term here is a 2, and there's a 1 down there, so you're thinking 2 over 1 equals 2. And I want to know if that's true, so what I do is, of course, take the limit of z going to 0 of 2 of 1 over z plus I, and 1 over z plus 1. Okay, so now everywhere there was a z here, I put a 1 over z. And now I want to guess, does this lead to the same limit? So I can do a little algebra here, z over z. I can multiply both top and bottom by this and go limit z goes to 0. And we see that's 2 plus I over z. Oops, sorry, wrong one. iz, there we go. And 1 plus z. And we can clearly just plug that right in. That's 2 over 1 plus 0, which is equal to 2. All right, so we've established that in this case it's continuous. There's no issues with a division by 0 or infinity over infinity, so we can just plug it right in, and we clearly get 2. All right, and finally 3. I want to now assess a similar sort of limit for the case of z going to infinity, and I want to know, here's another example of a 2 to z to the third power minus 1 all over z squared plus 1. All right, so I see that the leading order we have a third power in the numerator and a second power in the denominator, so I'm thinking this is probably going to be infinity. But what I'm going to do then is to diagnose that by taking limit z goes to 0 of 1 over f of 1 over z, which is limit z goes to 0 of 1 over z squared plus 1 all over 2 1 over z cubed minus 1. And I want to know if that's equal to 0. All right, so I'm going to do just like I did before. I'm going to multiply top and bottom by the same factor. And clearly what we have here is a z, so that's limit z goes to 0. We have a z to the first power plus z to the third power all over 2 minus z to the third power. And now this function is continuous at z equals 0, so I can plug 0 right in. We get a 0 plus 0 is equal to 2 minus 0, which is clearly equal to 0. So it checks out. And that implies then that the original function actually does diverge to infinity, so that's also a check. All right, so there's how we use this technique of evaluating limits at infinity. We have a way now of understanding what it means, infinity. Essentially what we're saying is if f is going to infinity, we put that in quotes, what we really mean is the absolute value of f is going to infinity. And if I want to take a limit, z going to infinity, and I put that in quotes again, what I really mean is the magnitude of z is going to infinity. And so now I have a concrete or a clear definition of what I mean by a complex number going to infinity. So thank you very much.